Bem-vindos ao Pavilhão do Conhecimento. Bem-vindos a esta sessão para os que nos estão a acompanhar através da internet. So, welcome to all of you who are following this session through the internet. But I can assure you that the session will resume very briefly in English. I'll just say some words in Portuguese for our hosts here at the Pavilion of Knowledge in Lisbon. Portanto, retomando, bem-vindos a este que é o primeiro dia C. O dia C será todas as últimas quintas-feiras de cada mês, fixem já, última quinta-feira de cada mês, às 7h30, o Pavilhão do Conhecimento Ciência Viva convida um investigador reputado na sua área, qualquer português ou estrangeiro, para nos falar de tópicos da atualidade. E que tópico seria melhor para começarmos este nosso ciclo de conferências do que a missão Rosetta? A missão Rosetta tem sido já comparada com a chegada do homem à Lua, pois representa um feito muito, muito difícil, aterrar num cometa e toda a informação que daí vai advir. E para nos falar sobre a missão Rosetta, ninguém melhor do que McCaughrean. McCaughrean, thank you for having come. McCaughrean é astrónomo da Agência Espacial Europeia e é uma das pessoas que mais sabe sobre a missão Rosetta e vai nos falar agora a seguir. No final poderão naturalmente fazer perguntas. Mark, the floor is yours. Thank you.
Thank you very much for that kind introduction, and thank you very much for everybody being here this evening. I can't tell you, I do this quite often, but I can't tell you every time how much of a privilege it is to stand up and represent the work of thousands of people across the world on one of the most exciting science missions, space missions, maybe ever. It has been an amazing, amazing adventure for everybody involved, and I'm just thrilled that everybody else participated. I want to take you through a journey this evening about why we even decided to do this in the first place. What's the meaning of a mission like Rosetta? Why would you want to study a comet? How do you do it? How do you catch a comet flying through space at enormous speed across the solar system? And how do you even dare to land on the surface of such a thing? I'm going to show you some of the results that we have. I'm going to show you some of the excitement that we've had in the world. And I'm going to tell you right at the end that this mission isn't over. Not at all. It didn't finish on the 12th of November. This mission is now in its most exciting phase as we're next to this comet moving towards the sun, and it's going to burst into life in 2015. So it's the beginning of a great adventure. We've had great fun already, but it's much more. There's much more to come. So let me start. This is a comet which you might have seen in the 1990s. Some of you aren't that old, I know. This is the famous comet Hale-Bopp, which was in our skies for 18 months. We could see this object. And those of us who did see it, we would love to see another comet in the sky like this, blazoning across the sky. But what we in the European Space Agency have done is not see one from a distance. We've gone right up next to one, and we're looking at it from a few kilometers away. This is millions of kilometers away. And why would we do that? Well, there's a whole bunch of themes which I want to touch in this talk this evening. We're exploring the universe around us, not just the comets, but also the stars, the planets, galaxies, all the way back to the beginning of time, the beginning of the universe. So exploration is in our spirit, in our nature, and you Portuguese know this as well as anybody else. Your famous discoverers, Magellan, Vasco da Gama, and others who sailed around the Earth, not even knowing if there was an edge to it, thinking, well, let's see where we get. Well, we're carrying on from that tradition by sailing out into the solar system with our magnificent spacecraft. But to do that, much like the shipbuilders, we had to build new technology. You can't go where we've gone without incredible dedication to building amazing pieces of engineering. And that's taken decades of work to get to the point where we can do these things. It's not easy. And we've only done it in Europe by cooperating between 20 countries within Europe and also with the United States and partners around the world. So sometimes, and you'll probably hear me this evening say, we've done something NASA hasn't done. We're proud of that, but we cooperate. The element right at the base of everything we do is cooperation between all of the European countries and across the world. And then lastly, and something which is a huge feature of Rosetta, is this idea of inspiration. We captured, I hope, the imagination of millions of people in the world through this adventure. And for me, that's what the most important thing is. It would be nice, it would be wonderful to share the science with you this evening, some of the early science. But what I really hope for is that you're inspired by a mission like this, inspired by what you can do when you put your mind to it, because we want to do more. We want to go on and learn our place in the universe in more detail. And at the same time, we have problems on the Earth that we have to solve, enormous problems. And we will solve those through science and technology and engineering. And we need to inspire a new generation to engage in those subjects, not to watch celebrity television, but to figure out, how does this world work? Why is the sky blue? Why do rivers run downhill instead of uphill? It sounds like a stupid question, but why do these things work the way they do? And that science, engineering, and technology that people will be inspired by will hopefully pull us through the eye of the needle which faces us. It's not very wide and it's not very far in the future. Because after all, it's been only a few 100,000 years since we were primates. And that's what we are. I'm sorry to disappoint you if you thought otherwise, but you are just clever primates. You are clever apes. And you differ in your DNA by 1% from chimpanzees. It's a very important 1%, of course, because it's that 1% which allowed us to work out that was just 1%, if you see what I mean. So it's only in the last 50 or 60 years that we've discovered the genetic code of our life and have been able to compare that to our nearest cousins, the apes, and all life forms. And we see what we have in common. And we see what we have that is different. And in fact, most of it is that we have in common. And so again, it brings this question of responsibility to the world we live in terms of the life that is here. It's fragile, and we need to work to preserve it. So that's the world we live on, but it has a place within the bigger universe. And how do we understand the universe that we live in? Well, this is a medieval woodcut, which actually it's not. It's an 18th century joke about a medieval woodcut that never existed in the first place. And then it was painted in the 20th century, so it's a kind of a pastiche of a woodcut. But it shows this idea of a middle-aged view of the world in the Middle Ages, where there was a kind of a dome above our heads with the stars painted on them. Objects moved across the celestial sphere, and somehow behind that there were mechanical cogs and gears moving and turning the universe around. But we understand the universe in much more detail than that. Much of the universe, of course, is so far away, we can never hope, we maybe can dream to go there, but in the near term we can't hope to go there. But luckily, these clever apes that we are, we've developed machines which can actually take us out into the universe, telescopes. We can look out at the stars, the distant galaxies, and all the way back to the beginning of time with our amazing huge telescopes. These are the Very Large Telescope, the 4 units of the Very Large Telescope in the Atacama Desert in Chile. And of course, these are not only machines that take us long distances, these are time machines, because every time we look a bit further away, we look a bit further into the past, because it takes time for light to travel to us. So the further away we look, the further back in time we look. So we can understand the birth, the evolution, the growth of our universe through our telescopes looking out into space. And the European Space Agency, who I work for, has a whole range of space missions which are dedicated to looking out at the universe from the very lowest, the longest wavelengths, radio wavelengths, studying the birth of the universe in what we call the cosmic microwave background, all the way to high-energy missions looking at gamma rays and X-rays, which study things falling into black holes. We're looking for planets around other stars. We're trying to understand the makeup of our own Milky Way. And all of these missions are returning enormous amounts of data that will come back next year, I promise you, and give a talk every week for a year about these missions. We have such a lot of science to talk about. Now, luckily, some parts of the universe are close enough that we can actually go to them. I'm going to make you a little scale model, okay? If I make my hands into a shape about this big, this is the Earth if it had been shrunk by 100 million. Okay, so I take the whole Earth and shrink it down to this size. That's the Earth. Now, I flew here today in an aeroplane. It was a bit bumpy, but you know. If I put on scale where that aeroplane was, it was the width of a human hair from the surface. Okay? Very, very close. The astronauts who are going around in the International Space Station today are 5 millimeters above the surface. And since 1972, that's the furthest we have been from the Earth. Just those 5 millimeters. Now, somebody's already done the maths. Where on this model is the moon? Somebody want to tell me quickly? Where is the moon in this scale model? My head? No? It's 4 meters away, over there. Okay? So, astronauts at the moment are 5 millimeters, and that's where they've been since 1972. But in the 1960s and the 1970s, they went all the way over there. There were 24 men, and I'm afraid they all were men, who went to the moon, and 12 went to the surface. And this is the last one. This is Jack Schmitt. And Jack Schmitt, he was the best astronaut of all who went to the moon because he was a scientist and not a fighter pilot. I told this joke recently, and somebody came up afterwards and he says, you know, I'm a fighter pilot and I'm an astronaut and I don't like what you just said. So. Jack Schmitt was a scientist and he was a geologist, and he went to the moon with a hammer and he found things on the surface of the moon that nobody had seen before. So we have done that. We have explored our nearest neighbor, the moon. But on the same model, Mars is 2 kilometers away. Mars is a long way away, okay? We all think that was the next logical step. When I was growing up, we went to the moon and we thought, well, by 1980, we'll be at Mars. Hasn't happened, and it won't happen for a long time to come, I'm afraid. It may happen in your lifetime, some of the younger people, but it's not going to happen tomorrow. It's 2 kilometers away in my scale model. But, fortunately, we clever primates have built clever robots. And this is a very clever robot because it's not only on the surface of Mars driving around with a nuclear battery, it's such a clever robot that it can take a selfie. This is NASA's Curiosity probe, which has been cruising around on the surface of Mars in the Gale crater, and it's now driving uphill to the mountain on the right-hand side, Mount Sharp, and it's finding signs of liquid water on the past in Mars. Not today, but we know that Mars had running water, oceans, rivers, and riverbeds, which we can still see today on the surface of Mars. So one of the hunts that is on is the potential search for life, or life in the past at least, on Mars. NASA has been very successful landing there, and we will be flying back to Mars in 2016 with 2 missions. ExoMars in 2016, which will sample the gases of the atmosphere from above, and then 2018, we will land on the surface, drive around, like this machine here, but we will do something different. We will drill 2 meters down under the surface to see if there are bugs still alive under the surface. What an amazing thing that would be if we could do that. But there are some people who think that's actually quite a stupid idea. Because if we go to Mars and we find life on Mars, it could be the same as the life on Earth. We could be exactly the same as Martians. And you think, well, what is he talking about? Well, we know today that if you look around the Earth in places like Antarctica, you can find small pieces of meteorite which came from Mars. We have bits of Mars in our hands already. I've had one in my office for a long time, a piece of Mars. I don't have to go there, 2 kilometers away, and I have it already. How did it get here? It got here because something big hit Mars in the past. Material sprayed out into space. That material flew around the solar system for millions of years, and some of it came to the Earth. The same will have happened from the Earth. Material from the Earth will have gone to Mars. So if life formed in one place or the other, it might have gone to the other place. And in fact, because the gravity on Mars is lower than the gravity on Earth, it's easier to get material off Mars than it is off the Earth. So we actually might really be Martians. Now, just don't look at the person next to you, okay? That's not fair. So some people think that a much more interesting thing would be to go here. This is Saturn, most majestic planet in the solar system, you could argue, with its massive system of rings. And it has an amazing moon called Titan. Titan is almost planet-sized, and it's covered in a dense coating of gas. We can just about see down to the surface. It's dense, it's cold, but it has the same atmospheric density, roughly, as the Earth on the surface. And we landed on this thing in 2005. We just celebrated the 10th anniversary. The European Space Agency's Huygens probe landed on the surface of Titan, the furthest anybody's ever landed away. And in my scale diagram, this is now 12 kilometers away. So we went out there, and we found a riverbed. Really? A riverbed, but not of water. A riverbed which had been cut by liquid hydrocarbons, ethane and methane, the stuff you might burn in your stove. This place is so cold that turns to liquid, and there is rain, there are rivers, there are lakes on Titan made out of liquid hydrocarbons. And maybe if we find life there, at the bottom of those oceans, that would be different to the life on Earth and Mars. Let me show you what it's like to land on Titan. This is the descent onto the surface. And you can hear it now. Here comes the sound. This is the wind of hitting the probe as we descend down to the surface. You can see river valleys on these sides here. You can see the way the delta has formed. You can see gullies here at the bottom where liquid hydrocarbons have run. This is an amazing place, and I'm sure we will go back to Titan in the future and explore it again. So we have a whole range of missions in the solar system, including at Saturn, Mars, Venus, studying the Sun, studying the Earth, and they're all encapsulated here. We're going back to Jupiter to study the icy moons of Jupiter and try to find out the properties of the oceans underneath the ice of these moons. Oceans, hundreds of kilometers thick of water underneath those crusts. We're also going back to the Sun, close up to the Sun, to study it in detail. We're going to Mercury in 2016 to study it, most enigmatic planet in the solar system. But over there, you see it, it's Rosetta. That's what I'm going to talk to you about this evening. So why would we want to study comets? What's exciting about comets when you can study Titan with its rivers and its oceans, when you can study the icy moons of Jupiter with 100-kilometer deep seas which might have life at the bottom? And why comets? They're only a few kilometers across. Why are they important? Well, for one thing, they're incredibly beautiful when they come across the sky. This is Comet McNaught. We didn't see it in the north, unfortunately, not in great detail. It was in the southern hemisphere. There is a comet outside tonight. It's called Comet Lovejoy. I don't know if it's clear out there, but there's a faint green comet just to be seen. If you get your digital cameras, you can take pictures of it. There's a tail. So there is a comet in the sky at the moment, but not one of these massive ones. But why are they interesting, Mark? Stop talking about them being beautiful. As a scientist, why would you go there? Well, they are leftovers. They're the rubbish of the solar system, left over from the birth of the solar system 4.5 billion years ago. We know that stars are born and die in our universe, repeatedly, endlessly. Stars are born, they give out their light, they die, they give their material back. That material gathers into clouds of gas and dust, which then collapse to form new stars. And around those stars, disks of gas and dust form and swirl around, and the planets are made out of those disks. But not all the material ends up in the planets. Some of it's left over. Our Earth has been so processed, tectonic plates, volcanoes, impacts. It's very hard to see the original Earth anymore. But if you can go and look at the old material that hasn't been altered much since the beginning of time, you can learn about the birth of our solar system from them. But you can do more than that, because one of the big questions about our solar system, and in particular about the Earth, is where the water came from. Where did water come from on the Earth? Well, maybe it was here all the time. Well, when the Earth was very young, it was incredibly hot. Everything was in the solar system when it was young, in the inner solar system where we live. So the Earth actually may not have had any water on the surface at all when it was young. So the water had to come from somewhere else later, from the outside. Nobody came with a bucket of water and said, have some water. It had to be delivered by something. And because comets are half water and half dust, it seems like an obvious thing that if comets hit the Earth, they would bring water. But we don't really know that. We have to try to measure the properties of the water on the Earth and compare it to that in a comet and see, did the water on the Earth come from comets? But it's even more than that, because comets have complex organic molecules, carbon molecules with hydrogen, oxygen, and so on, the stuff we're made of. In particular, they have amino acids, which are the building blocks of proteins, which are the building blocks of life. Comets have this stuff all over the surface. So it's possible that these same collisions that delivered the water to the Earth, or may have delivered to the water to the Earth, brought amino acids in. And in fact, there are theories and even experiments which show that as comets come through the Earth's atmosphere, amino acids get created in greater numbers by the impact. So we could be comet stuff. The water you drank today could have come from comets, and you yourself might be built out of the material which spent hundreds of millions of years in comets before hitting the Earth. So I think it's a good idea to go and look at a comet close up to find out the clues about our own origins. I mean, that's why we are doing this. Now, it's not forever, of course, that comets have been understood in this detail. For thousands of years, comets were said by many people, they were seen to fly across the sky, suddenly appearing out of nowhere, great tails burning across the sky, and people were quite afraid of them. People really didn't understand what they were. They didn't like change. This was something new. What's this comet about? People began to talk about them as, in English we talk about harbingers of doom. So that means something bad is about to happen. And in fact, this tapestry, which is the famous Bayeux tapestry, was something pretty bad about to happen for those of us who are English. This is when the Normans invaded in 1066. It's at this point I always say, and that was the last time it happened as well. But and this is King Harold on this side. These are people pointing up into the sky at a comet. That's a comet sewn into the tapestry. And it says, these men wonder at the star, this moving star across the sky. It turns out this is a famous object because in the 1700s, Edmund Halley was looking through the records of comets and when they appeared, and he found that some comet appeared every 76 years. And he said, well, it must be the same one. If it keeps coming back every 76 years, it must be the same one, going out into the solar system and coming back. Going out, coming back. He had the advantage then that he was a contemporary of Isaac Newton. And Isaac Newton had been working on his laws of gravity, and Halley could look at the orbit, the motion of this comet when it came through the sky. He predicted when it would come back. Its motions were measured, and it matched exactly what Newton would have predicted for an object on a big elliptical orbit going around the sun. So, hence this comet is Halley's comet. It was actually seen in 1066, and every 76 years since then. Now, it last came back in 1986. And that was good, because in 1986 we were well into the space age, and we were prepared to do this. This is a very famous satellite called Giotto. And Giotto was the first ever mission to get close up to a comet and study it in detail. So this is the European Space Agency's, one of its earliest great successes. Now, I just told you that comets do this crazy elliptical orbit. They go all the way out slowly, and then they fall in rapidly and go out again, rapidly, slowly. We live in the middle here, going around in circles. To get onto this orbit of the comet and follow it is really difficult. You've got to change your speed, and that takes enormous rockets to get onto the same orbit. We didn't have that in 1986. So what we did was say, right, we know where Halley's coming from. We know it's going to be here, then let's fly right past it at high speed, okay? let's not stop, let's just go straight past it. We can do that. And that's exactly what happened. So when Halley came in 1986, it looked like this, a tail coming out from it, but close up, right in the center there, Giotto flew right past it at about 600 kilometers away, at 6 kilometers a second, right past, and this is what we saw. The nucleus, the center of the comet, a few kilometers across, gas and dust spewing out on all sides. The big surprise, immediately, we knew that comets must be mostly made of water because you measure the tails of comets remotely with telescopes and it's full of water. But this comet's black. It's dark. Why is that? Nobody was expecting this. And we now know, as you'll see later on, comets are completely covered almost on their surface by dust. And that dust is material from the inside of the comet, which is pulled out. The water escapes, and some of the dust falls back onto the surface and slowly covers it up in dust. So comets are actually very, very dark. And that wasn't known until this picture was taken. Now, in the intervening years, we've flown past a number of other comets. We never stopped before because that's difficult, as I explained. This is Comet Wild 2 in 2004. The Stardust mission flew past this, captured some dust grains, some little particles from the tail, and brought them back to Earth to be studied. So we learned some stuff about the comet there. You can see it's a kind of a roundish shape, a few craters, mostly smooth, a bit potato-shaped. And here's another one. In 2005, an encounter with Tempel 1. Tempel 1's very boring, nice and smooth, lots of flat areas. And of course, this is what we thought comets looked like. Fairly ordinary, just potato-shaped. Now, what you can see here is something interesting if you've looked carefully. This side of the picture is quite blurry. The side of the picture is quite sharp. And why is that? Well, because this is actually an assembly of lots of pictures taken by a probe called Deep Impact. Deep Impact flew from here very fast past the comet. And it took lots of pictures. And as it approached the comet, it was able to take high-resolution pictures, which is on that side, and these are the pictures taken from a distance. But that's not all it did. It launched another small probe out from the front, in front of the one with the cameras on, and that probe went down and hit the surface at high speed. And the idea was to get underneath this dusty crust and pull up some material from underneath and look at it. And that's what happened. So this NASA mission went and blew a great hole in this comet. Actually, we went back later on and had a look with another mission. The crater's not very big, but it pulled a huge amount of material which could be studied by the other probe for a few seconds, and then by telescopes back at the Earth looking at this flash in the sky. But this is what we thought comets might be. And here's the last one I'm going to show you, which we flew past, because now you're beginning to see the comet activity. This is Comet Hartley 2. And there's something odd here. It looks like there's two parts on the right and on the left, which are lumpy, a bit lumpier, still fairly smooth, and in the middle, it's very smooth, very dusty. And we think this object might actually be two objects bumped together, not joined, but just touching under gravity, and then dust has gathered in between under gravity, but it's not compact or compressed. You could jump into it and swim in that dust there in the middle. That's why it's so smooth. But you're beginning to see some clues about activity on the comet, the material flowing out. So this was in 2010 and very important. But we wanted to go somewhere else, and we didn't just want to fly past for a few minutes. We wanted to go up next to a comet, fly alongside it, watch it change as it came through the solar system, and land on it. So which comet did we choose to do that with? Well, we did it with this one. It's got the lovely name 67P Churyumov-Gerasimenko. And it's named after the Ukrainian astronomers Klim Churyumov and Svetlana Gerasimenko, who discovered it. That's your privilege. If you go out tonight and find a new comet, it gets your name, as long as nobody got to it before you. And there are lots of people out there searching, so you'd better be good if you want to be the first. Mr. Lovejoy, who's out there tonight, I don't know how many he's discovered. He's an Australian amateur astronomer, and there's been lots of comet Lovejoys. It's not the only one. There's loads of them. I don't know how many children he has, but he has lots of comets. So, this is the comet, 67P, as we call it, because we just need to get the talk shorter. 67P has this odd orbit, just like many comets. It's an ellipse. It comes all the way out to the orbit of Jupiter and a bit beyond, and then falls in towards the Sun. It doesn't go so close to the Sun. It's not going to get destroyed by the Sun. In fact, it doesn't even get as close to the Sun as the Earth. It comes between the Earth and Mars. But that's a big change in the distance, and it's a big change in the brightness of the Sun. The brightness of the Sun changes with the square of the distance. So if you're 2 times closer, or half the distance, it gets 4 times brighter. So the amount of sunlight is much more when it's close to the Sun than when it's far away. This object was only discovered in 1969 by these astronomers, and it's got a funny history because in 1959 we can track back its orbit, and in 1959 it was very close to Jupiter because it's close to the orbit of Jupiter now, but there was a coincidence. In 1959 it came very close to Jupiter, and Jupiter is a big giant planet and has big gravity, and moved the comet, changed its orbit completely. For most of its life, 67P was much further away from the Sun, out by Jupiter, and it was pulled in by Jupiter in 1959. So we thought this would be a great comet because it should not have spent much time near the Sun. It shouldn't be very evolved. It shouldn't have had much melting or much sculpting of its surface. It should be potato-shaped and boring and flat and easy to land on. So we thought. It goes around the Sun every 6.5 years, so it's quite quick. We've studied it a few times. We can see what it does each time. It grows a big tail. Each time it comes around the Sun, it's a comet. Really is, I promise. And we could easily line up with it in terms of getting the right direction to go out into space. It wasn't quite that simple, because remember, we're going around the Earth in this little circular orbit, and we have to somehow get ourselves all the way out onto this big elliptical orbit. And I'm going to explain to you in a moment how we did that. But let's look at the spacecraft first. Here it is. This is Rosetta, not fully unfolded. The big box on the left-hand side, big square box, is Rosetta. It's about 2.5 meters by 3 meters, and it weighs 3 tons, or at least it weighed 3 tons at launch. Actually, half of that was fuel, and we've used most of the fuel in driving around, so it's lost a lot of weight on its way. Actually, when you lose weight, you usually look thinner. Rosetta hasn't got any smaller, it's just got lighter. I don't know if that counts, Sorry, I'm lighter, but you look the same. And here are the big solar arrays. And when they're fully deployed, these solar arrays are 32 meters across. It's the size of the wings of an Airbus A320. It's big, a big spacecraft. Why did we have to have so many big solar panels? Well, because we wanted to meet up with the comet all the way out near Jupiter. There's not much sunlight out there, so we needed giant solar panels to get enough power. No other spacecraft has ever operated this far in the solar system with solar panels alone. Every other spacecraft that's been out there has used nuclear power. We've done it on solar power. It's kind of the green European approach to life. And here is the big box Rosetta, and that's our beloved Philae on the side. All tucked up, legs together. So Philae, we always say it's a washing machine, and it weighs 100 kilos, and it's about this big. My wife would love a washing machine that big, because I have 2 children, and our washing machine needs several times a week. If it was 100 kilos and that big, it would just be one wash a week. But that's Philae, and here's the point. Philae is pretty small compared to Rosetta. Philae has very compact, small instruments on board. It's Rosetta that carries the big instruments, the ones that do most of the science. So everybody was focused and is focused on Philae. What did Philae do? Where's Philae? How's Philae doing? Rosetta is the real science machine, the driving most of the science. Philae's brilliant and has done this surface stuff. But don't think that because Philae is, how do I put it gently, currently not talking to us, that we're not doing science. Rosetta's doing amazing science every day because that's where the big instruments are. So, I'm a rocket scientist and I can't be here giving a talk without showing a launch video. And we have the sound up again? No, we can't. There we go. Can you just leave it up? It's a short video, but the point was that Ariane 5 is the biggest rocket we have. and it's one of the biggest rockets available in the world. And that rocket is nothing like big enough. It has nothing like enough power to get us on that orbit we want to be on, to get away from the Earth and get all the way out to 67P and follow it in. So we, clever little primates that we are, cheated. We said, well, let's just use this rocket, and then we'll be clever. We'll fly past the Earth. You'll see it happen now. And we'll steal a bit of the Earth and its speed. As we get close, the Earth's gravity will pull us in and then swing us past, and we'll get faster. And we did that 3 times with the Earth and once with Mars to get our speed built up and also to change our orbit from a circle into this big ellipse that we wanted to be on. You can see the probe, you can see the comet. The comet's even coming through here. It comes every 6.5 years. There it is with the tail. Oh, we didn't catch it this time. We'll get you next time. So in 2009, final time we went past the Earth. And then in 2008, we'd already done 1 asteroid flyby. We did another asteroid flyby in 2010. And then we were on the way. Now, I told you that we had these giant solar panels to get the power to work out there. We actually didn't have quite enough power to operate safely all the way out in the solar system, this distance. It would have worked, but if we had had a problem, we wouldn't have had enough power to reboot the spacecraft, effectively. So we made a decision. In 2011, we turned the spacecraft off. We turned most of its systems, most of its computers, most of its guidance systems, turned them all off to save power. Not save power, we just didn't have enough power. We left on some heaters to make sure that the lines with the fuel in didn't freeze, like you might leave your heating on in your... Well, sorry, you live in Lisbon, this doesn't happen to you. Where I come from, in the winter, we turn the heating on when we go on holiday at Christmas time because we don't want the water to freeze in the pipes. Actually, it doesn't happen in England anymore either. That's global climate change. But in order to keep it stable, we couldn't just leave the satellite standing there. We wanted to make it stable. And you all know one way of making things stable. If you take a little gyroscope or a little spinning top and you spin it on the table, it'll sit there going in circles. It won't just fall over. It'll be stable. It's actually how you can ride a bicycle. Have you ever thought about that? Here's a question for young scientists. How come you can ride a bicycle going in a straight line, but you can't stand up on it if you're not moving? You fall off a bike, most people. Most people fall off. I fall off a bike if I don't move on the bike. Have you ever thought about why that is? It's because the wheels are spinning, and that adds stability. So we spun up the spacecraft. We set it rotating, not very fast, but fast enough that it would stay stable. But then the big dish, the big antenna on the side, which we used to communicate signals back to Earth, started doing this. Oh. It wasn't pointing at the Earth anymore. So we couldn't communicate with Rosetta. So we left one more thing on. A clock, an alarm clock, which was timed to go off 2 years and 7 months later. And then we sat back and we waited. And I thought I would show you something. I wanted to talk to you a bit this evening about public engagement. This is public engagement. We made a decision in the end of 2013. The engineers said, oh, well, this is really risky, you know. We turned it off and it's going to wake up on January the 20th. But what if it doesn't wake up? Maybe we'll do this in secret, and if it wakes up, we'll tell everybody the next day, and if it doesn't wake up, we'll go skiing. And we said, no, come on. Let's get the world involved. Let's build this thing up. Let's see if people can help us wake up Rosetta. And so we made a few cartoons, and you will have seen some of them, and I just want to show you this one. I'll step from the stage. It's one of a whole series which we've made, and they've been very successful. I love them, and I'll play this one for you. Oh, no, I won't. I'm going to show you our flybys first. Sorry, that's why I have this thing, to tell me what the next talk is, the next slides. This is the Earth in 2005, 2007, and my favorite, in 2009. This is Antarctica from the back. We flew past Mars, and we did another one of those. Oh, here we are, we're at Mars. This is Philae taking a picture of Rosetta with Mars in the background, which is nice. So, you know, it's not every day. And here's the asteroid Steins, which we flew past in 2008. You can see we're getting closer and closer, and we fly past, and we see more shadows as the direction of the sunlight changes. And then in 2010, we flew past this guy, 130 kilometers across. It looks like we got really close. And it tells you something. We have a long telephoto lens on our camera. We were actually, luckily enough, 3,000 kilometers away at this point. So we didn't get that close, but it's a big object. And so, now, this is the mission Rosetta up until January the 20th. Sound? Hello? Sorry.
To uncover the mysteries.
Let's go back. We'll start it again.
Once upon a time, a spacecraft named Rosetta was launched into the night sky. A long, long journey lay ahead of her to uncover the mysteries of our solar system. Rosetta carried a little passenger, the lander, Philae. It had taken many, many years to dream up this mission, and now Rosetta was on her way to the far-off comet Churyumov-Gerasimenko. Rosetta needed lots of energy to get there, and got some from Earth and Mars by flying around them, seeing some beautiful sights. Along the way, she also went to places spacecraft hadn't visited before. Rosetta found a diamond-shaped object, the asteroid Steins, and took amazing pictures for everyone on Earth to see. The diamond disappeared as Rosetta sped on. Further along the way, a giant appeared. Lutetia, an ancient rock 100 kilometers tall and 100 kilometers wide with big craters on the surface. Rosetta sent more pictures home of the amazing encounter. This was still only the beginning of the adventure, but far from the energy of the sun, Rosetta was very tired and needed to rest. Still traveling through space, she fell into a deep sleep. A sleep lasting for 2 years, 7 months, and 12 days. Now it's time for Rosetta to wake up and open her eyes. Wake up, Rosetta! You and Philae have a comet to chase. Wake up! Wake up, Rosetta!
So we've made a whole series of these, and they've been translated and subtitled. I know they're available in Portuguese, and they've been enormously successful. And actually, the reason I sit down on the side of the stage each time I show that is because I have to actually take a little tear. It is amazing. It works on me every time. I suppose it was because I was there at the time. Oh, let's see what happened here. Okay. So, the reality. January the 20th, 2014, we were nervous because we knew when the signal was supposed to come back. And this is Andrea Camazzo, who is the flight director, and Paolo Ferri, who is the head of operations there in Darmstadt in Germany, where we run our spacecraft. There was actually, I don't know if you have it, the same phrase in Portuguese. In English, we call it a sweepstakes, where everybody put some money in a pot, and then you pick a winner of a sports, the World Cup or something. In the room there on that day, everybody had picked the time when Rosetta would send its signal back. And these were all the people who had worked on Rosetta for more than 10 years. They knew Rosetta and its computers and all of the things that might work and might not work. Was the system going to reboot? Were we going to get signals from this antenna or that antenna? So they all wrote down on a piece of paper. And I was sitting just over there on the left, on the side of the screen. And the first one came, the first time, and it was, 6:30, and it went past, and that was one person. They went, hey, whoa, you've lost. 6:34, oh, you've lost. Tick, 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 tick. We get to 10 to 7. Oh, 6:51. Oh, you've lost as well. Oh. We got to the last person, the last possible time for Rosetta to wake up. Tick. Nobody was laughing anymore. This was in that time. This was the half hour where, well, 18 minutes, where we just did not know. And then finally, the signals came in from Canberra in Australia and from Goldstone in the US. 2 antennas finally picked up the signal, and these are the same people. And you can see how happy we were at that time. These guys across the middle here invested most of their careers on this mission. This meant an enormous amount. And I'm going to let you into a secret. At that moment, Rosetta sent out a tweet to the universe saying, "Hello world," and it said it in all the languages, so it said it in Portuguese as well. And so many people said, "Oh, look, that's really cool. The spacecraft has got a Twitter account." See the young lady in the front row, Emily Baldwin? She's in my team. She has a Twitter account. So when Rosetta tweets, it's Emily. I'm sorry to disappoint you. I know that's not very romantic, but Emily's a lovely person. Don't think the worst, you know. She's desperately in love with Rosetta. So it was an enormous moment for us because that meant we were on our way. We were headed towards this amazing encounter. But we weren't there yet. We started to see the comet flying across the sky from our cameras on board, and we used these images to navigate towards it. And you can see by May, it turned into a comet for a while. Material started flowing away. So good. At least we were going to a comet. We didn't get to the wrong target. The GPS wasn't sending us to an asteroid instead of to a comet. But that worried us a bit because the comet wasn't supposed to be active this far from the sun. So we thought, oh dear, what are we in for now? Can we operate? Can we run a spacecraft next to this comet? Luckily, in the next picture, it stopped. So the activity went away. It was an outburst. But what it tells us, comets are unpredictable. They are not boring objects, dead objects. They change. And we have never done this before. We've never been up to a comet and tried to drive around one. It's a whole new game, and this told us to be careful. Now, remember what I told you about comets and what we thought they looked like? Boring potatoes? No. This is what we saw in June and July. This is the famous pictures which led us to call it the rubber duck. And I can tell you, scientists were thrilled, because look at this. If there are actually 2 comets there, joined together, we can study 2 comets for the price of 1 mission. Amazing. So scientists. Engineers? They were not looking forward to flying around this. It's not a boring potato. That means its gravity is different in all directions. It's difficult to fly around an object like this. And it moves. It's constantly rotating. There it is. It turns in 12 and a half hours. And when we fly around it, we fly slowly around it, and the comet's constantly turning underneath us, and the gravity's slightly changing. And we saw before, an outburst of activity could just suddenly occur, and all of a sudden we would be surrounded by a cloud of dust particles. So this again told us to expect the unexpected. This is in July, and we were racing up behind, or in fact we were in front of the comet, letting the comet catch us up. We were putting the brakes on, using all that fuel to slow down, to rendezvous on August the 6th. And of course, as we came close, oh, that's what we saw. Scientists, yay! Engineers, woo. Because look, I mean, what an amazing, astounding object. At the time, we did lots of media. By this point, because of the wake-up, everybody was really excited about this mission. They wanted to be part of it. We had lots of media, lots of TV. And I remember saying at the time, I said, we've arrived at scientific Disneyland. You know, we haven't even got out of the car and look at the object which is in front of us. I was on TV saying, yay, and all the engineers were going, oh, God. How are we going to land on that? Because look at it, it's got structure everywhere on the surface. I'm going to talk to you a bit more about how we picked the place to land, but let me just give you a sense of how big this object is. Katia has just walked around, and she's given, there's a couple of models of the comet. They are more or less miniatures of this, but how big is the real thing? Well, it's 4 kilometers. And we were at 100 kilometers on August the 6th, so I went onto the internet, our wonderful internet, and said, I want to see an object which is 4 kilometers in size from 100 kilometers for scale. This is Mont Blanc, and this lady is sitting exactly 100 kilometers away. I didn't take this picture myself. There, the internet has everything. And for scale, if we put the comet there, that's what it would look like. A 4-kilometer object, and we were 100 kilometers away. That's Lake Geneva in the foreground. So that's where we were. We weren't close. We were a long way away. And we stopped there to look at it and say, okay, how do we start flying around this? And then over the next few weeks, we started moving we started flying patterns in the sky in front of the comet to look at it from different sides and get closer and closer. And we worked our way down to 30 kilometers. Here's a sort of scary, if you don't like London, oh well, just follow the movie forward another few moments. But then we got closer and we were getting more and more details. Now it's a bit washed out in these pictures, but we were beginning to see amazing structures. This is the big body part at the bottom, which you'll see, and then the head at the top. And we're seeing what look like cliffs there, and we see boulders at the bottom of the cliffs. Well, I say bottom, but on an object like this, which way is down? Down is here. Down is here. Down is here. It's pretty much in the same direction all the time. But on a comet like this, where the mass, the weight is over here or over there, it depends really where you are, where down is. And we say those boulders rolled down the cliff, but actually now we think they didn't roll down, they flew off the cliff and landed at the bottom with the gravity and the rotation of the comet. And then we began to see things like this, sort of like mountains on the rim, and we see these boulders seemingly hanging on the side, but in this case, down is that way. But over there, down is that way. And then, we saw areas like this, which were big, flat, and smooth, and see these big boulders. Now, when they were at the bottom of the cliff, we could see maybe they fell off the cliff and rolled down or fell down, but where do these things come from? There's no cliff near to these. So are these objects which have moved from somewhere else? Or are they being uncovered as the comet, each time it comes around the sun, more material gets stripped away and these rocks or lumps of stuff get revealed from underneath? The biggest one you can see there off on the right-hand side with the shadow, we called it Cheops, after the famous pyramid at Giza. And I thought I would do something just to put this to scale, to make an image with the real Great Pyramid of Giza to scale in this picture. And it looks like that. Now, I did this one evening and I thought, the world needs to see this. And then I thought again, well, yes, but the world doesn't need this to come as an official image from the European Space Agency. There are enough conspiracy theorists out there already that this would not be a good idea. But I love this image, so I made sure a journalist friend of mine somehow got it in his inbox. And it found its way out into the internet. So if anybody ever shows you this and says there is life on, or there was dead life, I made it. I promise. It's not real. But we put all of our images out. We're trying to put more and more of them out, and these all from our navigation cameras. This really great amateur planetologist, Matthias Malmer, has made this fantastic rotating model. And you can begin to see the complexity. You can see that giant valley being carved through the neck. And we still don't know whether this is actually two objects joined together or one object which has been sculpted. Remember I told you that this comet hasn't been close to the sun for very long, only since 1959. So how can it have got so cut away and eroded in just those 60 years or so? So there's so many things we don't understand still, and that's why we're there now, still looking at it. And remember, we wanted to actually go and land on this thing. Now, you've seen, I'm showing these pictures. We all have Photoshop or something like it on our computers, and we take our pictures and we make ourselves look much prettier, right? That's what it's for. And we've made the comet look much prettier because we've stretched the contrast so you can see some white stuff and some dark stuff. But you shouldn't be fooled because these comets, I said earlier, are very, very dark. So let me give you a sense. This is one of the shiniest moons in the solar system, Enceladus. And the reason it's shiny is that at the bottom end of Enceladus there are cracks in the ice which are on top. And underneath the ice there's water. And water comes up through those cracks, shoots into space, and then falls back onto the surface of Enceladus as ice. And it permanently recoats Enceladus, so it's nice, clean ice on the surface, very shiny. So it reflects actually about 100%, nearly 100% of the light that falls on it. The Earth, on the other hand, is quite dark. It only reflects 30% of the light that falls on it. The Moon, you think it's white, but of course it's not at all. The Moon is really dark. If you think back to that picture of Jack Schmidt with his hammer running around, it's all very dark grey what he's running around on. It's not white the way it looks in the sky, because our eye adjusts to make it look brighter. The Moon only reflects 12% of the light that falls on it. 67p, there it is, I promise, 6% of the light that falls on it. So if you actually did that comparison properly, you really would be hard-pressed to see it. And in fact, it's one of the ways we've been looking for Philae, because Philae is a lot brighter, it's a lot more reflective than the comet. So if we can ever catch a glint of sunlight from Philae, it should really stand out enormously. So comets are really dark. But what color are they? Well, here is the comet, dark again. Now I'm going to increase the brightness, and I'm going to turn the color on. Okay? Oh. No, I did, honest. I turned the color on. It really is that color. It is incredibly gray. It's just dark, dark, charcoal-like dust everywhere. And we've been searching for signs of little bits of color on the surface. And in fact, at smaller scales, we see small signs of slight bits of blue. And blue is ice. There's not much, though, on the surface today. And that's because the comet's not very active today. It's got this big coating of dust on it. But in the next few months, that dust will be lifted off, and we'll see more ice underneath. That's the prediction. Keep watching. Now, of course, that happens because the comet gets active. So this is one of our pictures from the navigation camera, very stretched. You're seeing material. Even in November last year, before the landing, we're seeing material already. And this is still 500 million kilometers from the sun. It's going to get much hotter as it moves in. So we'll see a lot more activity. Another image, we're seeing this material lifting off. And here we're at 30 kilometers away. It's not a nice picture because it's been so stretched to see the gas and the dust. But it's already active. Okay. We're there. We've been studying it. We've been looking at it. We arrived in August. We had to land in November. We had just 3 months to pick a landing site and get down onto this amazing body. And this is one of the most iconic pictures, actually, it's another one of these. It's not really a selfie, because again, it's Philae taking a picture of Rosetta being photobombed by the comet. So it's very 21st century in any case. And we had to land in just 3 months. And you think, why were we so stupid to only give ourselves 3 months to land? Well, we couldn't get to the comet any earlier because we wouldn't have had enough power to run the spacecraft fully. Okay? Remember, we were out by Jupiter. Not enough power, couldn't run the spacecraft. So we had to wait till we were closer in, turn it on, get everything ready. But the more sunlight we have, the more active the comet gets, the more dangerous it gets to be there. So that 3-month window, we had to get there, look at it, pick a landing site, and land very quickly. Now, if you're an astronaut, I told you about fighter pilots, right? This guy, actually, he's a geologist. He's a very smart astronaut, but this is how he would land on a comet.
Got it. Admittedly, it's translating really slow, but at least we hit our comet.
There we go. So that's Alexander Gerst, one of ESA's astronauts on the International Space Station. This is part of a longer video in which it's a very nice video, actually. He's sort of trying to demonstrate, this moving object in the distance, and he's trying to hit it, playing darts, throwing. But it's actually very similar to what we did on the day when we landed. We weren't right next to it, and then we were a long way away, and we threw Philae like a dart at the comet. So this is a really nice. It's on YouTube. You can download it. So we had to pick a landing site. And we had to pick a place on this crazy-shaped comet. Because we're playing darts, Philae doesn't have any way of actually working out where to go. It's just like a dart, and you throw it, and if you're a really good darts player, you'll get in the bullseye. But I don't know about you, but I'm not that good, so I need that whole big board, right? I'm going to get somewhere on the board. So we predicted that we would be able to pick a circle 1 kilometer across, and we would land somewhere in that circle, somewhere on the dartboard, okay? But this comet's only 4 kilometers across. It's hard to find a place which is 1 kilometer across and clear of any bumps or lumps. So again, the pictures are a bit burned out in this projection, but you can see these are 1 kilometer squares now, and we picked these 5 landing sites, and none of them are flat and free of rocks. So we didn't like A very much. B, all these boulders are there. No, too many boulders. C is actually pretty flat, so we called that the backup landing site. And then we went for J on the other side. And in a public competition, that was then named Agilkia, which is a site in ancient Egypt, in modern Egypt as well, for that matter. And we wanted to land right in the middle of that. But you can see there are cliffs, and there are lumps, and there are bumps. And so it was always going to be less than 100% successful if we just threw a dart into that area. And if you look in more detail, we wanted to land, I don't know if you can see it, I'm going to put this red circle. Right at the center of that red circle is a roundish looking crater type thing, and there's a boulder on there. You see that? We wanted to land in the middle of that flat area. But remember, that's the bullseye. And if you hit the 19 or the 222 or something, you could fall on that cliff, you could fall on these big boulders down here. So that was the best we could do, and we started getting ready for throwing the dart. So we were, at that point, in orbit at 10 kilometers away. So this is spinning at 12 and a half hours, and we're going around. You see the probe. And then we moved away. We pulled back, and then we come back in again. And at a distance of 20 kilometers, we then turn and come down, and Rosetta drops Philae, and Rosetta moves away to get out of the way, and Philae goes down to the surface. And you saw the comet rotating throughout that whole thing. So it's not only playing darts, it's playing darts on a rotating, moving dartboard. And, it would be really pushed to get anywhere on the dartboard, right? So that's what we were trying to do on the 12th. It took us 8 hours between this point, where we first pulled back. This is the final picture taken by Philae looking back at Rosetta saying, "Thanks for 10 years of a great ride." But this is the last time they'll ever see each other, so it's this farewell picture. And then Philae descended towards the surface like a dart, just under the laws of Isaac Newton. Nobody was driving it. It was far too far away from the Earth for us to drive it. The signals were taking half an hour to come back. We couldn't drive it to the surface. And it did this. So here's Philae spinning away, followed down by Rosetta, taking pictures. And then we get close to the surface. You see the pictures taken by Philae coming down towards the ground. And that's where it touched down. Those 3 holes are where the 3 legs of Philae touch down on the surface. Of course, you'll see that Philae isn't there anymore, but you know that. Philae bounced. Philae did not grab the surface as it was supposed to. And we have this lovely movie here, which actually shows the place where Philae touched before, and then just after the moment of impact. Because what you see, that dark patch in the big red circle, is a cloud of dust that lifted up when Philae touched down. And then you can see Philae just off to the right, and its own shadow as they move across the surface. So Philae came in at 1 meter per second. Philae's 100 kilos, so I don't know. I've got to look for a big person in the room. If you're a big person and you walk into the wall, that's 1 meter per second is walking pace. If you walk into the wall, that's going to hurt, So there was a lot of momentum, but there's no gravity, or very little, and that gravity isn't going to grab you. So we had harpoons on board and ice screws to screw ourselves onto the surface. It didn't work. So the legs took some of the bounce out, and then off we went. Slowly. Boing. And what we think happened at this point is that Philae landed stable, came down, touched the surface, and then went off stable, but now turning. It has a big flywheel on the inside to keep it stable. So that flywheel was still turning, and we're going And then we think we hit a cliff and started tumbling. Then we landed. If we hadn't hit that cliff, we probably would have gone off into outer space and bye-bye filet. So that didn't happen. Now, if the sound is on, I'm going to play you something. This is the noise of touchdown. That was it. I like it. We'll play it again. Sorry, back one. That's in real time. That is vibrations in the legs of Philae recorded as sound as they hit. So it's not slowed down, it's not speeded up. That's as long as it took. In we went, off we went. So let's look at that in a bit more detail. Here we are. This is the point we're aiming for on the head, site J. It's about 1 kilometer across. We come down, we look in high resolution to see where we wanted to land. We wanted to land in that small circle just up away from the box, remember, with the rock in it? We landed 120 meters away. We hit the bullseye. We got the 50 points. And then we went down, you see the high-resolution pictures, and you can see the surface taken from underneath Philae just before we approached, from about 10 meters away. We saw this surface. Bang! So this is what it looked like from above. Here's Philae in a sequence of pictures descending towards the surface. It was actually descending more or less vertically, but because Rosetta was moving and the comet was turning, it looks like it's moving across the surface. So you see it, 3:15, 19 minutes past, 23 minutes past, you can see the touchdown point, a picture taken before it touched down, then after, the 3 feet. And then, right in the top corner, you see Philae deciding it didn't want to be there at all, off we go, leaving again. And it may have been just at the edge there that it hit the cliff, or a bit further off the picture. So as I said, we landed within 120 meters of where we were supposed to. Now, I'm going to indulge in political spin. I'm going to tell you this was a great thing to not land where we wanted to land. Because if we had landed in that rather boring place, it was all dust, it was nice and flat, but the scientists really wanted to get up to some of these cliffs where the exposed material is, okay? If we had landed where we were, the cliffs would have been miles away. This is where we actually landed, next to a cliff. Because we ended up tumbling and falling into a gap and landed right up against one of these cliffs. There's dust underneath us. This is one of the legs here of Philae. And then this is this cliff next to us. So we're actually about 1 meter away from this cliff. The problem with this location, of course, is that if you look in more detail, that's that picture there with one of the legs. There's another one of the legs at the top, the white patch. We put Philae in. We're actually perched up against the side of a cliff, and we're not getting a lot of sunlight into that location. We're in shadow. Philae had one big battery on board to do the first 3 days of science experiments, and it did them all. It completed all of those science experiments. But at the end of that, we needed to charge another battery. So if you like, you had a big battery, car battery, which was going to run out, and then you had your laptop battery, which needed to be charged up by sunlight. Okay? And to get the amount of sunlight in there and the amount of heat to even warm the batteries up so they could be charged, we needed 6 hours of sunlight a day. In this location, we're only getting 1.5 hours. So that's why the secondary battery didn't charge up, and it's why when the first one ran out, Philae went to sleep. It's not dead, it's just turned its systems off. Now, as we move closer to the sun's going to get brighter. The comet might turn. More light may well fall into this location. Enough light to heat up the batteries and then charge them up and turn Philae back on again. And we think, all current estimates are, that would be around May or June of this year. So Philae may yet come back to life. We don't know exactly where it is. We know from these images where it touched down, where we saw it last in that picture you saw before next to the cliff as it flew past. And we believe it ended up over here on the rim of this large crater over here. Somewhere. And you can see on the right-hand image, it's a bit more refined. That yellow streak is where we think Philae is, somewhere in there. We've been looking, taking high-res pictures. We haven't found it yet. But as you can imagine, if it's in a dark, shadowed place, you have to be at exactly the right time of day to get the sunshine in there to see it anyway. So we've tried, but we're probably going to stop now because by constantly flying over the same place. We're not doing science the way we want to. So we're going to move back now, and we're going to stop looking for Philae for now. We're going to see if Philae comes awake later in the year. We'd like to know where Philae is, and it's important for some of the science, but it's not critical to the mission. So we're going to stand back now. So please stop writing into us and saying, have you found Philae yet, and when are you going to tell us, and how you're looking for it, and everything else. We tried, and we appreciate, and we hope for it to wake up again. So let's move back to November the 12th. Here's just one picture of the elation. I mean, I could show you videos and all sorts of things. I mean, it was an astonishing moment. I mean, really, for everybody. There are many of the primary people here involved. You see Andrea in the middle there, Paolo, who I talked about, the flight directors, Elsa, who is one of the spacecraft operation managers, Fred in the back there, who has his hand up. He's the mission manager. He's in charge of the whole machine. And these two guys in the jackets, they're the people in charge of the lander from the German Space Agency. In the background, you see, smiling and right behind the glass screen, Matt Taylor, who's the project scientist, and then Manfred Warhout, who's the former head of operations there. He's been on this mission for a long time. He's a happy guy. And for those of you who like education, there's Paxi. I think that's our education mascot right down in the front, celebrating. And so at that moment, I was off on doing live television and to the BBC. And actually, it's a little-known story. There was another. This isn't the main control room. It's the big control room at ESOC in Germany. But the one where Rosetta's really run from is somewhere else. This is for show. This is TV. And that control room saw the signals first. And I was standing outside of that control room of the BBC, and we heard the cheers, and we went, what? What's going on? Oh, we must have landed. 5 seconds later, they started cheering, so we got it first. But I got quite emotional at that point and threatened to hug the BBC journalist, and she was fine. So the next day, of course, I mean, there's so much I could show you, but I mean, just as one thing, just newspapers around the world, pictures of the comet, this success, this amazing story. The world really got heavily engaged in this, and we're really appreciative. At some point, it took a life on of its own, though. I mean, we worked really hard in my communications team, who deserve an enormous amount, not just Emily who saw, but all the team who put so much together to make this work across the agency. But we couldn't have believed the amount of publicity and the amount of interest that we had. So again, I'm just showing you the newspapers here, and even the Washington Post and the Wall Street Journal, So, but as we approach the end of the year, things, people begin to reflect. People look back. News for one day or news for 3 days with Philae. But we couldn't really have expected some of these things. Here we see the front cover of Science magazine, breakthrough of the year. We have a Google Doodle, which was done on the day, showing Philae descending. That's a funny one, because Google had told us they wanted to do this. You go to the Google search page, homepage, around the world, that's what you see. And we knew they were doing it. And on the day, we were there, we were ready, we were descending, and we said, oh, but it's not up yet. We sent an email. Well, it's today, it's not tomorrow. And they sort of replied, yes, but we're only going to put it up when you successfully land. So there's the faith they had. It doesn't even show the landing. I'm not even really sure I saw the point. But and they did another one for us. You can see there at the end, on one of the events of the year, 2014, Philae landing on the comet there in 2014. The British Royal Mail, every stamp, every letter that went around the UK for 2 days, 3 days, was stamped with congratulations to the European Space Agency. We are talking about the United Kingdom here, who doesn't like saying the word European very often. So this is a major achievement. Andrea Akamatsu, the flight director, one of the top 10 people in the world who mattered for the science magazine Nature. And I want to show you 2 videos, one from Facebook and one from Google. Again, they're end-of-year summaries to show you, again, just the sort of... I don't take credit for this, but I am very proud that we did this. So here's the... Hello? We're having trouble with the sound. Can we put the sound on, please? Not that one. Ready? I'm ready. You're ready?
The most powerful force on this planet is human cooperation.
Stop defining each other by what we are not, and start defining ourselves by who we are. We can all be freer.
and then the Google one, which is a bit weirder. I'm sorry, but it's Google.
Did you hear those words?
Just rendezvousing with this comet is an extraordinary thing. We're going to make discoveries that no one's imagined yet.
So, you know, the impact of this mission in terms of inspiring people, grabbing people around the world has been just a huge reward. I'm going to show you one last thing as a hint in the bottom corner. You can't quite see it. The 13th Annual Visual Effects Awards, a ceremony in Hollywood on the 4th of February. I'll come back to what that's for in a moment. But let me just finish in the last 10 minutes or so, 5-10 minutes, talking a bit about the science, because that's why we went there. I'm a scientist. We went to do science. We went to this amazing object, and we went with this big orbiter, and we have instruments all over it. We have instruments which take pictures in different wavelengths, visual wavelengths we can see, the ultraviolet, the infrared, radio wavelengths to look beneath the surface. We smell and sniff the stuff that's coming away from the comet. The comet smells dreadful, by the way. It smells like a horse stable. It's got ammonia, it's got the stench of urine, it's got hydrogen sulfide, it's got cyanide. We have thought, marketing-wise, that Odor Comet 67P might not sell in the world's airports, but, you know, the real geeks would be into it. Smell me, I smell like a comet. And we're measuring the gas and dust as it flows away. We're actually catching that. I'm going to show you a picture of some dust we've even caught. We catch the dust and look at it through microscopes. We also measure the plasma, the gas which has got its electrons stripped away from it, emanating from the comet, and we measure that. And then when Philae landed on the surface, it had its instruments, of course, as well. Cameras to look at the descent, microscopes to look at the surface, these pictures you saw from the surface. We looked at the material. We're digging up the material and sniffing it and putting in little ovens on board, little laboratories to measure its properties. And we drilled, we hope we drilled, we think we drilled below the surface. We're still not sure. The drill went out. Whether it went into anything, we don't know. And we hammered the surface to see what it's made of as well. And one of the great experiments, which we really hope for, if it comes back, we got some data, was we beam radio signals between Philae and Rosetta through the comet, through the body. And by doing that, we can, like when you go into a hospital, well, I hope you don't have to go into hospital to have tomography, but if you do, you can scan the inside of your body, okay, by putting signals through it. We did the same thing. Beaming signals through the comet, we can see what it's like on the inside. And we have to send the data back to Earth, of course, so you beam radio signals back, but we not only collect the data, but we measure the speed at which the signals get to us. And of course, that's the speed of light. But if the spacecraft's moving one way or the other way, it's a little bit more or a little bit less. We can measure the movement of the spacecraft to 0.2 millimeters per second at 500 million kilometers away on an object moving at tens of thousands of kilometers an hour. It's amazing. And if we can do that, the reason if we measure that, then we measure how the comet is pulling the spacecraft around. We can measure how much the comet weighs. And we know the comet weighs 10 billion tons. It's a lot. But it has a volume, we can measure its size, it has a volume of 21 cubic kilometers. Somebody do the maths? How much does it weigh? What's its density? If I had 1 cubic meter here and filled it with water, anybody know how much it would weigh? 1 ton. If it was made of comet, it would weigh 470 kilos. Less, half of water. It would float. If I put it in a big lake, this thing would float, bob half above the water and half below. Real ice, an iceberg, is 10% above and 90% below. Normal ice is much denser than this. And we've measured now its density. We know it's made of water, ice, and we know it's got dust. And if you kind of calculate what that should weigh, we can actually work out how porous this object is. If you take snow, for example, when snow falls, have you heard of snow? Sorry, that's my southern European joke. Snow, when it first falls, is very light and fluffy, and then it gets compacted later. It's the same stuff, but it's the porosity, how much air, how much gap is there between. The porosity of this object, overall, is 70 to 80%. It's 70% to 80% empty space. Not in big holes, not giant caves or anything, but it's just very lightly packed together because the gravity is so light. And I'll tell you a little story about gravity just in a moment when we get to the end. So we've named all the regions now. Some papers came out last week where the scientists working on the mission have finally named regions. Rosetta, of course, is named after the Rosetta Stone, which was discovered in Egypt, and it's the clue to the hieroglyphics. And so there's an Egyptian theme running all the way through. I told you about Cheops, for example. So these are all Egyptian mythological names or places in ancient Egypt. Imhotep, for example, you may recognize the name there. So they all have region names. And here's one picture close up from just 10 kilometers away or so, showing the amazing detail as you look up and pan up to this astonishing cliff-like structure. Okay. From the top peak there down to the base of the cliff where you see the rocks, that's 100 meters. Okay? So everybody who's young would say, let's go to 67p and go base jumping. The most boring base jump you will ever witness, because the gravity on this comet is about 100,000th of the gravity on the Earth. If you stood on the top and launched yourself out, it would take you 20 minutes to get to the bottom. And you would arrive at the bottom at a speed of 20 centimeters a second, which is this speed. So you don't need a parachute. Not that the parachute wouldn't work, there's no air, but you don't need one anyway. But you'd have to be careful, because you know base jumpers, when they jump, they not only go out, they go like this, right? The gravity is quite weak on this comet. So I'd like you all, if you could, briefly, to stand up. Can you all stand up? Because I'm going to teach you how to jump off a comet now. Everybody can do this. Grandmas, grandpas, children. You only have to jump to a height of 4 centimeters. If you can go 4 centimeters high, 1, 2, 3. Now, you just jumped off that comet. So, when you made your base jump, you would have to be sure and not push up, because you never would land at all. You would just fly forever. So, that's the amazing thing about this comet, is it looks like it's rock and it's cliffs and it's solid and it's hard. It isn't. It has very low gravity. It's mostly ice, not very compact. It's a weird object. What you think it looks like doesn't tell you what it really is. You need to do the science. We've had people telling us this must be a real rock. It's not a comet at all. There are theories of, well, they're watching on the live stream, so I can't say the name of the people who claim this is definitely a rock, not a comet. I'm sorry, guys, it's a comet. And the comet's mostly made of ice. So what we've done, of course, high resolution, this is a pit, it's a hole. These craters you see are not craters created by impact. We think there's only one place we can see a picture on the comet where something's hit it. All these other craters are actually caused by heating. When the sun heats, pockets of gas build up underneath and then explode. We haven't seen that yet because we're not close to the sun. In the next few months, we may see explosions rising up. But I'm going to turn the contrast up here. Look. See? There's jets coming out of that hole already. There's already material coming out from that hole. And look at this one. This is just mind-boggling. This is another one of these holes. And look at the texture of the surface inside, under the surface of the comet, down that hole. It seems to be bumpy. I asked somebody today, but in Portuguese, what do you call these things when you're cold? And, sorry, Portugal, you don't get cold. All these Northern European references. Chicken skin, exactly. So look at it. It's bumpy and rough, and those bumps are about 3 meters. All of those lumps seem to be about 3 meters in scale. What's that telling us? Is that telling us about what the comet's made of on the inside? On the surface, that's all been changed by the sunlight, but maybe on the inside, it's all these lumps and bumps of objects made in the early solar system, about 3 meters across, which have bumped together and then built up the comet. So just in a picture like that, we're beginning to learn about how this comet was put together. And on the right, this side here, on the left-hand side, you can see the bumps on this cliff as well, the same sort of scale. We know how the comet rotates. We know where it's, like on the Earth. We have a North Pole, a South Pole. We know how it spins. We've been measuring that. I told you about the gravity. We've measured, and the gravity is different across the whole comet, not only because the mass is different, but because the comet's rotating, if you're near to the outside part, which is rotating fastest, the spin of the comet will actually reduce the gravity by quite a lot. So even though you would think the highest gravity would be on the biggest bodies, not by the neck where there's not much mass, actually the gravity's strongest there because that's the bit that's spinning least. So again, you just have to change your thinking about these objects. And I told you about, the gravity's changing everywhere. You can see on the comet, depending on where you are on a slope locally, where's the gravity? Is it pointing down 30 degrees away? And that's a map of where the gravity is pointing on each point in the comet. And here's an interesting one. There's a crack in the comet, a big crack. It's about 500 meters long in the neck, and we're not quite sure yet whether that's because the comet is getting weaker there and under the very weak gravity is about to collapse, or it would be even cooler if it broke in two. Not just because it would be cool, but because if it did, then we would suddenly see into the crack in between and we'd see the material which is inside the comet without being altered by the sun. So watch this space. Maybe it happens this time around. I told you we'd captured some dust particles. They're amazingly fluffy. We catch them at about 1 meter a second as they come away from the comet, and then they collapse, they fall into pieces, and we can measure them. And we can actually, these are about half a millimeter across. They fall into little piles of particles, and we believe these are dust grains left over on the surface from the last time we went around the sun. And then those grains will be blown away now, and new grains will come out from underneath, new dust, and fall back on the surface, and each time we'll have this cycle. So we're measuring the grains. I told you we're measuring plasma as well. This is a scientist plot. It's lovely, don't worry about it. It's the interaction of the wind from the sun with the comet. And one of the most successful pieces of outreach was turning this into sound. Hint to the people in the back. Could we turn the sound up? You couldn't hear this with the human ear. It's about 10,000 times changed in its frequency. But we're hearing the comet interacting with the sun. I like this thing until it gets a bit freaky at the end and a bit scary. So I turn it off here. Thank you. It's been listened to 5.5 million times on the internet. It's amazing. It's been used in lots of sound, some music and so on. So here's one of the big science results. I'm right at the end now. I told you right at the beginning, comets. Were comets the origin of the water that we drink, that you're made of? How would you know that? How would you study that? Well, on Earth, all water has mostly, it's H2O. We all know that. Everybody knows water is H, 2 hydrogen atoms and 1 oxygen. Except there's a little bit in there of heavy water. Deuterium with hydrogen and oxygen. Deuterium is a hydrogen atom with an extra neutron chucked into it. So there's a fixed ratio of that. You see that blue line on the graph? About 1 part in 10,000 of all of the molecules of water you drink actually has deuterium in it. It's not poisonous, don't worry, okay? Don't panic. But that's everywhere on the Earth. So, if we look at asteroids, most of them have the same value as the Earth, but they're very dry objects. There's not much water in an asteroid. But most of the comets ever measured in the past have more deuterium in them than the Earth's water. Except, I showed you a picture of Hartley 2, the comet that had the 2 parts with the smooth dust in the middle and the water flowing out. That has exactly the same ratio as the Earth. So a few years ago when that was first measured, people thought, oh, maybe it is comets again, maybe it is comets. So we measured 67p, and unfortunately, it's way up there. Much more deuterium in 67p than the Earth's ocean water. So we know that, in fact, the water we're made of didn't come from comets like 67p. And even more specifically, it didn't come from 67p because it hasn't hit the Earth. And it's never going to, don't worry. So, for me, when we thought about how do we tell this story, everybody would be disappointed now that we're not comet water. Actually, it's better this way. because it was always clear that the water on the Earth couldn't come from one family of comets alone. We've been hit by lots of asteroids. We've been hit by lots of different kinds of comets. If the answer had been yes, exactly the same, that science would have been dead for 20 years. Everybody would have said, oh, water on the Earth from comets, thanks very much. The science is now even more exciting because we're still searching for the answer to this question. That's the trick scientists pull. We never answer questions, we always ask new ones, and we move on and do the next thing. So, 67P and that kind of comet, the so-called Jupiter family of comets, is not the origin, or most of the origin of the Earth's water, we don't think. But it's just one comet. Hartley 2 is another Jupiter family comet, and it has exactly the right ratio. So it opens this question, which kind of comets fell, when and how and what time, what period. And that's the lead in here right to the end, because this comet is going to burst into life, and we're going to study so much more about it this year. This mission isn't over. We've just seen the beginning, an amazing beginning, but just the beginning. And we're really excited for what happens this coming year. And I really hope that you and everybody else, live stream, everybody else out there, follows this mission, because it has been this hugely inspiring thing, not only scientifically, but for the general public. And I love this picture of a father showing a young child Comet Pan-STARRS a couple of years ago in the sky. So if you do have young kids, or if you're young at heart, go out, find a dark place, see if you can see Comet Lovejoy this weekend. We have a lot to do. We're at 30 kilometers today. We're going to start flying by. In February, we're going to fly 6 kilometers over the surface on a kind of a... We're not going to go into orbit. The closest we'll ever be, so that's coming soon. We'll be the closest point to the sun in August this year. The comet should be fully active. We run to the end of this year, and then we have enough money for the end of this year. We'll push into next year, I'm sure. And at the end of that, we have to decide what to do, because we don't want to put Rosetta back into hibernation. We didn't enjoy it the first time. As the comet moves back away from the sun, we've got to do something else. So remember that big trench? Okay? Anybody seen Star Wars? Yeah. I think we'll fly through the trench, and then we're going to land, maybe. We're talking about landing Rosetta on the surface of the comet. The big machine. It probably won't work after we land on the surface, but what better way to go out? I think it'll be very cool. So you can all follow the mission. There's lots of social media. And I want to finish with one last thing. I know I've taken lots of your time. I'm passionate about this mission. We did one other special thing. I talked about Visual Effects Award in Hollywood. We've been nominated for what you're about to see. Something we decided we wanted to speak to the world, not cartoons, not the facts. We wanted to make something which was about the inspiration of the mission, a bit about the scientific goals, but fundamentally about one word: ambition. About seizing the goal of doing something audacious, of going somewhere and doing something nobody had ever done before, about being able to fail and learning from failure, but hoping for success. It's a short 5-minute film that we made with our friends from Poland, and I'm personally very proud of it. It's not a science film, but hopefully you'll enjoy it. And you can see it downstairs. There's a subtitled version in Portuguese if you want to see it again, which I hope you will.
Enough. Walk with me. Perhaps we should find you something a little less challenging.
I don't understand. I planned everything. Let me do it again.
Once upon a time.
Really?
This is a good one, I promise. What is the key to life on Earth?
Water.
Water. For a long time, the origins of water, and indeed life on our home planet, remained an absolute mystery. So we began searching for answers beyond Earth. Where could all this water have come from? In time, we turned to comets. 1 trillion celestial balls of ice, dust, complex molecules left over from the birth of our solar system, once thought of as messengers of doom and destruction, and yet so enchanting that we were to catch one. A staggeringly ambitious plan.
Are you talking about the Rosetta mission?
Throw me the probe. We harnessed whole planets and their gravity to chase down the comet. So many things could have gone wrong. A failure at launch, an error in the calculations, collisions, so many unknowns. With the technology we had back then, we may as well have been shooting from a slingshot. And tell me, what was it all for?
Knowledge.
Yes, but we also wanted to show what was possible.
I know all this from the archives. There were bigger missions after.
Yes, it was the first one to catch a comet. Ambition. Stubbornness. Nothing has changed. We fall, we pick ourselves up again, and we adapt. I was watching you earlier. You actually did everything right. I destroyed your rock. I needed to see how you would react. You're ready. Reset. Nicely done. Let's begin.
And so with that, thank you very much, ladies and gentlemen. I have been immensely proud to be involved in this mission and to bring it to you this evening, and I hope you follow on. Proud on behalf of the whole European Space Agency and everybody we work with and our partners. Thanks very much. And it's not over yet. Obrigado.
Obrigada. Dado o adiantado da hora, vamos aceitar apenas 2-3 questions.
Sure.
2 ou 3 questões.
Alguém tem perguntas?
What will determine the end of the Rosetta mission?
Sorry.
what will determine the end of the Rosetta mission? It had an expected end. Is it because the activity on the comet? Is it because of the power on board of the spacecraft?
It's many things. That the activity we can actually deal with, we can move further away. So we will be moving back now. All the nice close-up pictures you've seen at 10 kilometers or so, we'll do this final pass at 6, and then we'll move away as far as 100 kilometers. And that will also, the power should be enough whilst we're in this phase for the next year, but as we move back out again in the solar system, we have less power. We would have to go into hibernation again. But the main thing is fuel, because we have fuel on board. Every time we change our direction, we use fuel. And in fact, a little known story, we had to get rid of Philae. We had to get rid of it because otherwise we would have been carrying around dead weight with us everywhere. So we were really relieved even when Philae left, because then we were not carrying this weight around. So we're using the fuel now to fly around, and we won't have much left. And we don't really think we want to go back into hibernation and come back again. So that's why we're talking about maybe landing on the comet as the end, rather than running out of fuel. Because the last thing we want to do is run out of fuel and not try that. So, or something cool like that anyway. Yeah.
So, hello. Well, I have two questions. I don't know which one to decide. One is more political, another one is more, it's rather technical, so I'll go for the political one.
Okay.
Nowadays, how do you put 20 cooperating countries to work together? And what would you say in that terms to the young people out there that want to be a part of ESA or its missions? What would you say to them? And how do you think this cooperation is important? What are the struggles?
Well, it is absolutely the result, as I said at the beginning, of good cooperation between our member states. We have 20. We are not the same as the European Union. There's a lot of overlap, of course, but we have some countries who are in the European and some countries who are not. So, but it's Europe in that sense. Plus our Canadian friends are involved. And we don't always agree with each other. And of course we have some big countries and we have some small countries. The amount of money that comes into the European Space Agency for science is directly related to the amount of GDP, how much money you have. So you would think, well, that means the big countries dominate ESA. But no, because the voting is actually done one per country. So Portugal, Greece, other countries have the same vote as Germany, France, the UK. Now that's, it's not always comfortable. It's not, it can be awkward, but that's how politics is, and it's how cooperation is. We have to work together and we resolve our differences and we do amazing things at the end of it. Sometimes it could be a bit more efficient, maybe, and people say, why do you spend this much money on something like exploring comets? We don't send money into space. We spend it here in Europe on high-tech jobs with trickle down into the economy. So there's a lot of very important industrial and political aspects, and it works. We've worked successfully. We're expanding. We're adding new countries. People want to join ESA because of the success. And at a time when the European Union is I wouldn't say the European Union itself is struggling maybe, but people's attitudes to the European Union is struggling. ESA, I believe, has been a symbol of success for Europe. Not for the EU, that institution, but for how we can work together. I am old enough, and many people in the room are old enough. We think we live in this post-political, wonderful world of Europe where it's not so long ago things weren't like this. And the way Europe is today and things that we have done in this short period, this mission stems back to 1985, half the way back to the end of the Second World War. So the planning has been in place for a long time. How do people get inspired? Well, you said, how do people get into ESA? You're in ESA. You've paid for it. You are part of ESA. So that's why I've come here and why you're welcome to engage in this mission. It's your mission. Young people, well, somebody asked me in a TV interview earlier on, how would you get people inspired in science? I have one answer to that. I hope this has inspired people, but go outside and ask questions. Why is the sky blue? As I said before, why do rivers run downhill, not uphill? Become curious. That's what you need. If you want to work in space or in science or in engineering, be curious, be engaged, think, plan, but be excited by the opportunities that may be there. And if it all works out and you don't get more interested in neuroscience or DNA studies or plant technology or climate change, come and work for us. It's not, I say, it's that easy. It's hard. There's a lot of study involved. But, you know, we've got a huge range of people in the agency, nearly 4,000 people of all of the countries, different skills, not only rocket scientists and engineers. We have legal people, we have people who work in administration, we have financial people. There's a lot of ways of being closer to this amazing thing. Again, I'm privileged. I get to be right at the front and stand and talk to you about it. But behind me, there are thousands of people who did all the hard work, which I can bring to you and talk about. And you should be proud of the European Space Agency. We do amazing things.
Mais alguma pergunta?
Hello, thank you.
Thank you.
After, you think it's possible after you land Rosetta still communications?
Well, this is the thing, you know, Philae has feet. Philae was designed to be a lander. And I have to be careful, because every time I say we might land on the comet, I go home and people say, oh, you shouldn't really be saying that. We haven't decided yet. The thing about Philae talks to Rosetta, and the signals go back from Rosetta back to the Earth. So it doesn't matter really how Philae lands. It only has to talk over tens of kilometers, as long as Rosetta is able to link back to Earth. So if we were to land Rosetta, the big antenna would have to somehow be able to point to the Earth. So we actually would have to land it upside down. So the antenna, well, you could figure out, because the antenna's on the bottom of Rosetta. It wears up and wears down in space, you know. So if we landed it the right way, that the antenna was still movable, there's at least a slight possibility we might be able to point it at the Earth. Each 12 hours, the Earth came around. But it's, you know, that's where we get into the science fiction. We will do our best because we've done amazing things already, but we are so successful on this mission already that the engineers are raring to go.
Thank you very much for your nice talk.
Thank you.
As far as I understood, Rosetta flew about 2 years in hibernation mode.
Yep.
And in this region, between Mars and Jupiter, there is a region full of asteroids.
Yep.
During this time, you were afraid of collisions, or
no.
Or you have any control system to prevent this kind of things?
No. Looking at you across the room, I wouldn't say you have seen Star Wars too many times, but you know, even in our science fiction film, Their Ambition, we painted all the comets close to each other. The asteroid belt is not a dangerous place in that regard. There are lots of asteroids, but it's extremely big, so they're not close to each other, the asteroids. We know where the big ones are. We actually deliberately flew past 2 of them, Steins and Lutetia. We maneuvered to get close to asteroids. So very small things, of course, you know, dust particles and so on, we probably got hit by some of those, but we know where the big things are in the asteroid, big enough to cause us a lot of damage, and we weren't taking pictures at that point, so there was always a chance, but statistically, asteroids are so far apart in reality, they're not crowded, you don't fly through them in the Millennium Falcon like that, but it's cool, but yeah, it's not that dangerous in the asteroid belt, really.
E vamos terminar por aqui. Há mais uma pergunta, muito breve, por favor.
Considering Rosetta was not meant to land in the comet, will it be able to send us as valuable data as Philae was capable of?
Yeah, exactly that same point. As long as if we could, we would have to land it with a communications antenna still pointing at the Earth. And we would have to be able to, when the comet rotates and the Earth comes into view, point at the Earth. Rosetta itself has this big dish, and it can keep the dish pointed at the Earth as it moves. But as the comet's turning, the dish would have to be constantly moving to point at the Earth. So it wouldn't be so easy at all. But we'll see. Maybe in the end of 2016, I'll come back and tell you how it worked out.
Vamos terminar aqui. Aproveito para dizer que o próximo dia C é o dia 26 de fevereiro, última quinta-feira de fevereiro, e que teremos aqui connosco o Henrique Leitão para nos falar da ciência dos descobrimentos do século XVI. Portanto, para quem gosta, como vocês, de viagens e de exploração, aqui têm uma oportunidade para virem ao dia C, sendo que agora a viagem é também no tempo e não só no espaço. Agradecemos mais uma vez ao Mark. Mark, thank you again.
Thanks.